The first lecture. Carlo.
Thank you, Keith.
I should perhaps announce your title, The Properties of Quantum Turbulence, the Homogeneous Isotropic Case.
So good morning. I would like to thank the organizers for inviting me here today. I would like to describe some basic properties of quantum turbulence with emphasis on the relation between the ordinary turbulence and quantum turbulence. And before I start, actually, I would like to mention my collaborators. I'll give you some recent results obtained by Andrew Bagley, Lucy Sherwin, Yuri Sergeyev, and Jason Lowry. So my title is When Quantum Becomes Classical. So I'll describe the context, which is superfluid helium, quantum vortices in superfluid helium, what we mean by quantum turbulence, turbulence in Bose-Einstein condensate, and concentrate on two main properties of homogeneous isotropic turbulence away from boundaries, the simplest case, the energy spectrum, and the velocity statistics. And I'll try to draw some comparisons with ordinary turbulence and see how we can learn a bit about, we can learn a bit from quantum turbulence and make sense of what we know already about ordinary turbulence. So deconstructing, essentially, turbulence. So, first of all, what is the context? The context is usually very cold matter, from liquid helium, liquid superfluid helium, to ultra cold atomic gases and other systems which undergo Bose-Einstein condensation. I'm not going to describe the physics of Bose-Einstein condensation. Simply recall that from the point of view of the hydrodynamics, the major property which should interest us this morning is the fact that there is a complex wave function which describes the system, a complex wave function psi. So psi has an amplitude and also a phase. So immediately we seem to come across a problem, because if we apply the ordinary rules of quantum mechanics and write down a velocity field, we find that this velocity field must be proportional to the gradient of this phase. And therefore, the vorticity, which is the curl of this velocity field, must be equal to 0, because the curl of a gradient is always equal to 0. So you may ask, oh well, how can you have then vorticity? How can you have turbulence without vorticity, actually? I'll show you that, yes, we can, perhaps. So first of all, let me describe what is a vortex. A straight vortex, a vertical vortex in the pictures which I'm going to show, away from boundaries and other vortices. The amplitude of this wave function in the vicinity of the vortex looks like in the picture. So it's uniform far from the vortex. As we approach the vortex line, which is straight and vertical in this image, this amplitude goes to 0. In fact, the vortex is defined as the region where psi is equal to 0, both real part and imaginary part. So a vortex is some kind of hole or funnel, which you see here, this tight region where psi goes exactly to 0. But there is more to that, because besides a hole, we have also some flow around the hole. And to have the flow, we need the phase, the quantum mechanical phase, to change from 0 to 2 pi, going around our hole. So in conclusion, our quantum vortex is a hole with circulation. We do not have vorticity, we have circulation. And I'll argue that we are going to get turbulence simply by having holes with circulations. From another point of view, we can think of our quantum vortex as a tiny textbook tornado. Why is that? Well, first of all, it's a very simple, therefore, textbook kind of system because the viscosity of the fluid is equal to 0. We have a superfluid. Secondly, the circulation, which is the integral of the velocity field around the axis, is actually fixed. This quantity is very important. It's a measure of the strength of the vortex, is equal to kappa, this constant kappa, which is proportional to Planck's constant. And that was actually demonstrated experimentally in some remarkable experiments by Joe Winan in 1961, that the circulation can only acquire this value. So there is a unique way of having our vortices. Thirdly, the vortex is actually a very one-dimensional object. The hole, the region, the size of this funnel is actually very small. In superfluid helium, for example, the typical diameter is of the order of 10 to minus 8 centimeters, 1 angstrom. So that is atomic thickness. The length of the vortex can be as much as you want. If you have a large apparatus, say 1 centimeter, 10 centimeters, then your vortex line can be even that big. So we have a very large aspect ratio, a length which is perhaps millimeters or centimeters, and a core size which is atomic. So really one dimension. So if you put things together, lack of viscosity, fixed circulation, essentially one-dimensional objects, you really get what you find in the books like Lamb's or simple fluid mechanics books. You have a vortex line with a velocity field which is proportional to 1 over r, as indicated here, and these vortex lines either terminate at boundaries or free surfaces, or they're closed and they make some kind of loops. So this is what I mean by a quantum vortex. Now it's important to compare the properties of quantum vortices to the properties of vortices in general. So imagine we create a vortex by stirring our cup of coffee with a spoon, or take another larger vortex, for example, Hurricane Sandy. Well, if you measure the rotation law, the velocity around the axis, you will find something which looks like this. So it's a very arbitrary shape. It changes from vortex to vortex. And there is actually, in general, only a very narrow region in which the velocity field is 1 over r, because there is nothing generic. It changes. There are also situations in fluid mechanics where vorticity does not look like tornadoes. So we don't have actual some evident rotation. Imagine, for example, the flow of a river between banks, or some kind of shear flow like this airplane is experiencing while landing. So here we have vorticity, but we don't immediately see the rotation. So classical vortices, ordinary vortices, are more complicated. We have viscosity, we have dissipation, and rather arbitrary shapes. Quantum vortices are simpler from this simple point of view, the geometry and the strength and the lack of dissipation. Now, once you have your superfluid, for example, superfluid helium, and you want to make turbulence, well, the task is somewhat easy, because any kind of disturbance will actually create vortices, and if you insist, turbulence is easily generated. So here there is a list which is imperfect because there are other methods, but it's a list of ways in which you can create the turbulence of vortices. You see that various techniques have been used, from applying a heat flux to stirring by means of grids and propellers, to rotating the system, etc. So these are actually laboratories nowadays where there are current experiments, and this list is perhaps not complete. How does the turbulence look like? Well, I've taken an image from numerical calculation, which you see here. This is done in a periodic box, as we often do in fluid mechanics. So you see like a tangle of spaghetti. Yes, these are actually the vortex lines. So it is a snapshot, because these objects keep moving, rotating around each other, reconnecting, waving, do many things. So when you think of turbulence, you should imagine something like this. Notice that these lines are not actually physical objects. They are simply the region of the axis of the vortices, around these lines, you must picture there is flow which is circulating with the same strength around each line, and there is no viscosity anywhere. What do people measure? Well, a variety of things. There is a quantity which is often rather easy to measure in these systems, which is called the vortex line density. That is the vortex length in a given volume, L. From that quantity, we can recover approximately the distance, the typical distance between vortex lines. And that I shall call this quantity delta, the separation between vortices. And it's useful to stress the very large separation of scales which we have in these experiments. So I call psi the thickness of a vortex core. Now that quantity is fixed by quantum mechanics. As I said, it's about 1 angstrom in liquid helium. Delta is the separation between vortices. I would say in many experiments it's something like 10 to the minus 3, between 10 to the minus 4 and 10 to the minus 2 centimeters. And capital D is the system size, the size of the experimental cell. That can be centimeters. So we have many, many orders of magnitude in going from the core thickness to the intervortex distance to the system size. Therefore, it makes sense in some numerical simulations to think of our vortices as one-dimensional objects without any thickness. Now, to give you a flavor of this turbulence, I would like to show you a little movie which is the result of a numerical calculation done by Andrew Bagley and Lucy Sherwin. So we have a periodic box, and you see the injection of some vortex loops which interact with each other, reconnect with each other. You see these loops which wave, there are waves, and at some point the lengths of these vortices saturates because we're compensating with the injection, which is continuous with some dissipation, and we have some kind of statistical steady state, which is what we call quantum turbulence. I stress, what you see is only the axis of the vortex lines. Imagine the fluid which is spinning around each line with a fixed strength, with a fixed circulation, and it is actually fluid without viscosity. So I would say that this is this picture makes apparent that this system is ideal for studying the topology of turbulence, but because you see the skeleton of the turbulence directly.
Could you entertain a question?
Yes?
I don't see anything at a scale that's angstrom scale.
No, because there isn't. This calculation was done using a model in which a vortex line is taken as a filament. So it's one dimension. There are other calculations in which we can resolve what happens at much smaller scale. But here, essentially, the basic length scale is the separation between the vortices, and what you see are lines. They are thick to be visible. Okay? There is no resolution.
You don't see kinks at curvature corresponding to the angstrom scale, though.
No, they are not. There is a bit of dissipation in this particular numerical simulation, so you will not get kinks at that scale. With the other models, you will see actually these very, very short length scales being excited.
Filaments have all same circulation.
Yes. So that's how do we stop it? That's the important property to remember, that the filaments have the same circulation.
How do you inject? You say you're injecting vorticity.
There is some dissipation in this system, in this numerical calculation. So if you let the vortex lines to evolve, eventually you will be left with nothing. So to model a continuous forcing, which is done in the experiment in various ways, for example, injecting loops by means of essentially injecting ions, or stirring by propellers or grids, some rings are injecting constantly at uniform rate into the system. It's a numerical injection. Yes.
Just to make the point here, this is counterflow turbulence here, so it's finite temperature. There's not little wiggles, and the vorticity is injected from an instability with the normal fluid essentially is passing energy into the superfluid. So there's no vorticity injected by hand here.
Okay, there is another.
Is that by a solar?
Yes.
There is another system which is very similar, which people study seeking turbulence, and it is ultra-cold gases. So these are atomic Bose-Einstein condensates, and they have different properties, sort of unique properties. First of all, the density is not uniform. They're rather small systems, and they are not homogeneous. The atoms are confined by some quadratic trapping potential, and they look like this. So what you see here is the density profile of a condensate, which is this red curve, and there is actually one vortex which is placed somewhat off-center. So the picture in the xy plane looks like this. Dark red means high density, blue means zero density. So you see the non-uniform profile, and this hole is the vortex, the hole with the circulation. You don't see the circulation because I've not plotted the phase. So this is an atomic condensate. You can create vorticity, quantum vorticity in atomic condensates, and I want to show a couple of pictures. At the left-hand side, there is an experimental picture. You see a condensate, and the holes are actually a vortex-anti-vortex pair, which are moving back and forth, oscillating inside the condensate. At the right-hand side, you see a numerical calculation. It's a three-dimensional calculation. Pale blue is the surface of the condensate outside of this small cloud of atoms. In purple, you see the funnels, the tubes of the vortices. You see they are tangled spaghetti-like. So this is a snapshot because they keep moving and agitating. And already you see from these two images the important feature of turbulence vorticity in atomic condensates, that we do not have the very large separation of scales between the core thickness psi, the distance between the vortices, and system size. So psi is less than delta, which is less than capital D, but it's not much less. Okay? So we have a very tight confined system. So a natural question to ask then is, can we create turbulence in these atomic condensates? We can create vortices. Can we call it turbulence? How many vortices do we need to call something turbulence? We know that just few vortices, for example, in 2 dimensions, with our boundaries, 4 vortices, we have chaos, but that is not turbulence. Turbulence actually is more. At which point we go from chaos to turbulence? That's a good question which we would like to answer by studying these systems. There is another feature of atomic condensates which is important. They are tunable. Unlike superfluid helium, we can change our interaction parameters. We can actually change even the sign of the interaction parameter between the atoms. So we can almost do what we want. So it's very nice actually to control and change the properties of nature, sort of engineer the flow which we want. And finally, a very important feature from the point of view of the fluid mechanics is that we can easily change the dimensionality. We can move from 2 dimensions to 3 dimensions by simply squashing the system or not in a way which is not possible really in any other system. So clearly we know that in fluid mechanics we have different properties in 2 dimensions and 3 dimensions, and here we can actually control this dimensionality very well. So a good question to ask, that there is work at the moment being done, is about the 2-dimensional reverse cascade. That is actually the flow of energy backwards in k-space from the large scales, from the small scales to the large scale, which is responsible, for example, for Jupiter's big red spot. So people are trying to achieve this cascade in 2-dimensional atomic condensates. So let's go back to the tangle of vortices, of which you've seen this little movie, I want to highlight some of the physics, the phenomena which go on inside. There are actually many things. It's a fascinating problem. For example, reconnections. There are many papers, recent papers on reconnections. Just want to remind you of a recent paper by Kursa and Konrad Bayer, Thomas Lipniaki, studying reconnections of quantum vortices using different models. So reconnections are really crucial for turbulence because they scramble, they randomize the velocity fields, and in these systems they are discrete. We can count reconnections one by one. So they can be studied in this context very well. So similarly, the result of the reconnection is the making or the unmaking of knots. So vortex knots are objects which we find in these systems in an actual fluid mechanics system in which we use water. It's more difficult. We're going to hear about that later in the workshop. Here, essentially the system itself has a very clean topology because we have either a vortex line or we don't. So we can define knots very well. Kelvin waves, which are the modulation, the ondulation along the vortices, are another property which is important. They're called Kelvin waves because it was Lord Kelvin who first described their properties, derived the dispersion formula in the late 1800s. You see here some vortex rings which have waves and they move at different speed. The emission of vortex rings or vortex loops in general is another process which is important in the dynamics of the tangle. Typically, it comes about from reconnections or self-reconnections of vortices, and there have been papers recently by various people, in particular Bob Kerr's paper. If we look at some smaller scale, also other effects are very interesting. When vortices move at high frequency, they can produce sound waves. That's classical fluid mechanics. But this radiation actually means losses of kinetic energy. In this picture, you see actually two vortices of the same polarity which rotate about each other, and this pattern is the actual sound wave which is generated. Sound waves are also created by reconnection events. What you see here in blue are two vortex lines which have just reconnected, two antiparallel vortices which have just reconnected, moving away from each other, and you see this sound burst which is emitted in a special direction. So many things are going on. But I want to go back to liquid helium, which is the major prototype problem for quantum turbulence. It has been studied for longer. And remind you that in superfluid helium, we have actually two fluid systems. We have not only the quantum vortices, part of the superfluid fraction, we have also a normal fluid fraction, which consists essentially of thermal excitations. The amount of thermal excitations depends on temperature, as you can see in this graph. So this is the fraction of superfluid in blue, the fraction of normal fluid. So those two fractions change between 1 and 0, between absolute 0 and the critical temperature. And in superfluid helium, a number of similarities have been found experimentally between quantum turbulence and ordinary turbulence. So today I would like to try to not to describe these results per se, they are interesting per se, but also see how we can actually think backwards. It would be nice, in fact, to reconstruct the properties of fluid mechanics from the combined effect of many single discrete quanta. Can we actually do this reconstruction? Essentially, how many elementary quanta we need to reconstruct classical behavior? That is what I'm aiming at. So one of the first property of the two which I want to consider is the energy spectrum. The energy spectrum is an important property if you want to study simple turbulence away from boundaries, isotropic, homogeneous, driven in a steady fashion. It is the distribution of the kinetic energy over the various length scales, which we parameterize in terms of a wave number, the inverse length scale. So we know that this distribution is the following. We can take the total energy, the kinetic energy by integrating the velocity field. We fully transform the velocity field, and this distribution in k space is the energy spectrum. So in steady turbulence, it looks like this, plotted log-log. There is quite a large region in k space where the distribution of kinetic energy follows this log k to the minus phi divided by 3. That is the famous Kolmogorov scaling, which is in the middle region, if you want, in the middle region between the length scales at which energy is fed into the system, typically a very large length scale, and the small length scale at which the energy is extracted. It is extracted because if you look at the governing Navier-Stokes equation, then the viscous dissipation term, which contains the viscosity and the Laplacian of the velocity field, becomes as important as the inertia term. So at this length scale, energy is lost and becomes heat. But in between these two scales, the very large one and the very small one, we have some transfer, some cascade transfer of energy from big eddies to smaller and smaller eddies. Essentially, vortices get stretched, smaller scales are created, and energy is passed on. And we have this distribution k to the minus 5/3. Now, the same distribution was observed in superfluid helium, first by Patrick Tabelin in Paris more than 10 years ago. And this is the picture from their paper. It was found at different temperatures, even at rather low temperatures, about 1.4 Kelvin, which corresponds to probably 7% normal fluid only. And then experiment was repeated by other people, in particular by the group led by Philippe Roche in Grenoble. You see various plots done in Grenoble. So we want to understand why there is such a classical result in a two-fluid system, which is actually rather different. Now, together with this spectrum, there is another spectrum to consider. It is the spectrum of the fluctuations of the vortex length. It's a major observable in our system. The vortex line density length per volume L in a steady state will consist of a mean value, plus some fluctuations delta L. And if we measure it versus time and take the frequency spectrum, we'll get some typical power law, which seems to scale like the frequency to the power minus 5/3. And that's typical of a passive object which is advected by the turbulence. And it is actually remarkable that the same property is observed in helium-3, which is a different superfluid at much lower temperatures, essentially pure superfluid. This experiment was done in Lancaster. So we have to account for these two phenomena, the spectrum of the energy and the spectrum of the density fluctuations. Now, the models which we use here are either the Gross-Pitescu equation for a Bose-Einstein condensate, which will be described by other speakers, or the vortex filament model, which essentially is these equations in these slides. So we are treating vortices as filaments with no thickness and let them interact in a classical way via the Biot-Savart law, which is this formula, and add a reconnection procedure, which is justified by what we know about the system from the Gross-Pitescu equation. And in modeling this way superfluid helium at finite temperature, we find indeed both results. We find indeed that the energy spectrum has this scaling, which is minus 5/3, which describes some kind of partial polarization, as it was described first by Jovinen in his papers, some partial polarization of vortex lines over length scales, at least up to a typical wave number 2 pi divided by delta, where delta is the separation between the vortices. At larger wave numbers, the spectrum is different. Clearly, we are zooming into the system. We're looking at details which are much smaller than the distance between vortices. We see straight vortices, so we tend to see k-1 spectra, which are typical of straight vortices. Now, this vortex filament model also predicts a spectrum for the density fluctuations, which is consistent with what has been observed. So this is a rather noisy picture, but you see the same same scaling, roughly, which is frequency to the power minus 5/3, seen at high temperature in Grenoble and low temperature in Lancaster. Now, the beauty of numerical simulations is that it allows us to play with ideas and not only reproduce experiments, but try to make sense of what we have. So, I remind you what I said at the beginning, that our vortices do not have a vorticity. We have only holes with circulations, and we're treating the holes as filaments. So to define a vorticity, we could, for example, take the vortex line density, vortex length per volume, and multiply it times the quantum of circulation, and then from the dimensional point of view, we would obtain a vorticity. But clearly that depends on the orientation. A vorticity is a vector field, it's not a scalar field. So imagine that you take some vortices which are parallel to each other, like in this picture. So the whole rotation is in the same direction, and clearly these three vortices aligned together generate some large scale rotation, and we can make sense of some vorticity, we can define it. But if the vortices are in three random directions, then the vorticity does not make any sense. It's as a vector field is 0, because there is nothing which is happening on the scale which is larger than the vortices. So we need to distinguish between vortex length and vorticity. Vortex length physically has to do with dissipation. The presence of the vortex introduces dissipation and coupling with the normal fluid, for example. So how can we do it? Well, we can do it by using numerical procedures. Either we can convolve the vortices with some Gaussian kernels with typical length scale of the order of the vortex separation, or spline fits, etc. And here is a numerical example of this exercise done by Andrew Begley. So you see here at the top, you see two vortices which are wiggly, but they are actually aligned in opposite directions. So essentially they cancel each other out. We're getting a vorticity which we can define a vorticity which is almost 0. It's not exactly equal to 0 because of the wiggles, but it is almost 0. Vice versa, at the bottom we have two vortices which have the same polarity, so together they build actually a vorticity field, and indeed you see that it is a much more intense signal. So armed with these numerical tools, we can actually decompose our vortex tangle into two parts. So this decomposition actually dates back to some years before this numerical experiment. We call this decomposition, the decomposition into polarized and unpolarized vortices, L parallel and L cross. And that is very clear from the pictures. On the left-hand side, you see the entire vortex tangle, at least at a fixed moment, a snapshot of the vortex tangle. At the right-hand side, you see the vortex lines which actually correspond to the coarse-grained, numerically defined vorticity, which is non-zero, which is large, and second picture at the right, to the vortex lines which are actually randomly oriented. They are unpolarized. So together these two parts make up the entire vortex tangle, but what is interesting is that this decomposition can actually remain stable with respect to time. You see at the top the vortex line density on a log-log scale, the total vortex line length, and the polarized part, which is actually a rather small fraction of the total part in this experiment. It's only about a fifth, and it remains constant and fluctuates. So it is indeed what was actually argued by Jovina, that it's some kind of partial polarization of the vortices which is taking place inside our vortex tangles. So what is actually the consequence? Well, actually it's important, because it can explain the major experimental evidence. It can explain the Kolmogorov spectrum. In fact, if we take all our vortices and compute the Kolmogorov spectrum, we get, as I said, the minus 5/3 law. Now we can actually tune the threshold which we used, numerical threshold which we used to define polarized and unpolarized vortices, and lower it, and then we go from the Kolmogorov spectrum to the k-1 spectrum of naked vortex line. So clearly, actually, the polarized vortices are responsible for the minus 5/3 spectrum. But what about the frequency spectrum of the vortex line density? Well, if you just plot the total, the spectrum due to the total vortex length and the spectrum due to the polarized part, you see that they are very different. The polarized part drops much faster. So it's the random vortices which are responsible for the frequency spectrum. So this is the physical distinction actually between polarized and unpolarized vortices is actually visible in two different experiments, and one should not be misled by the fact that the exponent which we find, 5/3, is actually rather similar. So I said already that we have this polarization of the quantum vortices, and this picture shows again the vorticity, the coarse grain vorticity here, this large scale polarization. And I think it's worth mentioning that this distinction, in spirit at least, is similar to another interpretation which has been given by Marie Farge, Kai Schneider, and collaborators to classical turbulence. I remind you of the exercise, the numerical exercise which they did about 12 years ago. So they took some numerical simulations of ordinary turbulence, and you see a snapshot of vorticity regions. They used wavelets to decompose the field which is responsible for these large-scale coherent structures and the incoherent structures, so coherent and incoherent, and they found that it is the coherent structure which gives the Kolmogorov spectrum, and the incoherent structure gives a random spectrum which is k square. So at least in spirit, our the composition which we apply is the same. We have the coherent part which gives the Kolmogorov spectrum, and then the incoherent part which gives a random spectrum. From our point of view, this spectrum which is random would be the spectrum which scales as k2-1, the spectrum of individual vortices. Now all this is true and good for rather high temperatures where we have a normal fluid to introduce dissipation. What happens when the temperature is very low, like in the experiments in Lancaster? Well, essentially what we see from the numerical simulations is that the same properties can apply. Not always, it depends exactly on how we force the system, but we can actually produce tangle of vortices like you see in this picture, which have a Kolmogorov spectrum, which contains regions of intense vorticity, and whose frequency spectrum of the vortex length scales exactly at higher temperature. Now there is, however, some new physics which is taking place at very low temperature, and I want to tell you about this problem because it's quite important. Without friction, really, there is no limit to the length scales which can be created, and a mechanism takes place, interaction of Kelvin waves which produce smaller and smaller waves. As I said, without limit, well, eventually there will be a limit because the vortex coordinate, which is atomic in thickness, will introduce an ultimate cutoff. But before we reach that point, some kinetic energy will be turned into sound simply by classical mechanisms of sound emission. So some dissipation must exist at this very short length scale. But what happens in between? Because we find that there is quite a range in length scales between the scale of the distance between vortices and the scale of the photon emission. Well, here is where actually a Kelvin waves cascade can happen. This nonlinear interaction of Kelvin waves which produce shorter and shorter waves. It's another cascade process, so transfer of energy to smaller and smaller scales, but it is actually taking place not in 3 dimensions, but rather along individual vortices in 1 dimension. So it's these waves on individual vortices. Various papers have been written on the subject. The hot problem is what is the spectrum of these Kelvin waves. Some theories have been proposed. It seems to be that there are various regimes in these Kelvin wave cascades, strong regimes and weak regimes. The theories, of course, become rather difficult in the strong regimes, but at least in the weak regimes, wave turbulence theory can help, and there are predictions. And among the various papers, I would like to mention a very recent one by George Pustulovic, which has just been published, and he has actually confirmed some theoretical prediction of Lvov and Nazarenko on the amplitude spectrum of this Kelvin waves cascade. There is also another prediction which was made, that there should be some kind of bottleneck between the Kolmogorov spectrum and the Kelvin wave spectrum. A bottleneck is a region in K-space where energy piles up. Just to illustrate it, I've taken this picture by a paper of Srinivasan, where a compensated spectrum is plotted showing the bottleneck between the inertial part of the spectrum and the viscous part of the spectrum. You see this rise, which is zoomed here. This is what I mean as a pile-up of energy. Well, the prediction is that there should be some bottleneck. So going from the Kolmogorov energy cascade to the Kelvin wave cascade, this pile-up of energy, there is recent work based on the Gross-Pitaevsky equation which attempts to see this bottleneck, and the evidence is slightly in favor, but this is still an open problem. So I see that I don't have much time left, so probably I'll skip over the second property of turbulence. Just mention briefly that also velocity statistics can be measured, and in classical turbulence the statistics are Gaussian. In quantum turbulence they can be measured directly. Remarkably, it was done first by Srinivasan, Lathrop and collaborators in Maryland, and they found PDFs which are actually non-Gaussian. They have very high curvature, and they've been measured also in Grenoble using very small pitot tubes. And here we have actually a contrast between experiments in Maryland and experiments in Grenoble. So in Maryland, non-Gaussian statistics detected by very tiny tracers, about 1 micron size, a distance much less than the separation between vortices. In Grenoble, classical statistics measured with pitot tubes larger than the separation between vortices. Again, the numerics can help because one can measure the velocity statistics over some integration region, say capital delta, and we go smoothly from this non-classical power laws to the classical statistics, so depending on the scale at which we look. So if I come to a conclusion for this morning, what is the conclusion? The conclusion is that we see actually the appearance of classical behavior in terms of the energy spectrum and the velocity statistics, provided we look at length scales which are slightly larger or significantly larger, depending on the situation, than the typical vortex separation. So as you see in this picture, if you look at regions which contain many vortices and then consider the energy induced by the vortices in this region, or the turbulent velocity field which is arising from this region, we recover essentially classical behavior. So many quanta construct classical behavior, exactly as we expect from the qualitative theory of Bohr, of the original quantum mechanics of Bohr. So many quanta reproduce classical behavior, and we know exactly how many quanta really, because we can measure them. If we actually have individual vortices, we have a very different kind of behavior. For example, these non-Gaussian statistics. We have the Kelvin wave cascade, and so on. There is clearly much work to do in this field, because the numerical simulations, which I've just described, for example, highlight some phenomena which have not been observed directly. For example, the existence of vortex bundles, of coherent regions of quantum vortices. They have not been seen in the experiments. We need to think of some ways of searching for these structures, if they exist, of course. The Kelvin wave cascade is only a theoretical idea, numerical idea. Again, there is no experimental evidence which is direct, which we have. The reconnections, which is perhaps the ultimate the ultimate quantity which is responsible for this phenomena, has been seen directly in the experiments, but not the Kelvin wave cascade. Also, the bottleneck, which has been speculated about, has not been seen directly. So this is really a list of work to do, and I stop with this conclusion that with many quanta, we recover the fluid mechanics, which we are trying to learn the hard way, this way. Thank you. I'll stop here.
almost out of time, I'm afraid. Could I, well, we have one or two questions, ask Bob to come up and, for the next lecture, get his slides ready. Are there any questions, comments? Go. Yes.
Is there any connection between the coherent structures and intermittency? Because intermittency has been observed in its effect on the higher order structure functions. And what is that telling us?
Yes, it has been observed by Tabeling.
Yes.
He reported actually some results, and this is something which should be done more systematically. So perhaps there is indeed a connection, but clearly we need more work in this respect. That's the natural place where to look for this effect, this intermittency.
I should say it's very good to have Joe Vinan here. It's the sort of 50th anniversary, 51st anniversary of the paper that was referred to there. So wonderful to have you, Joe. One question here.
Is there any range of scales where vortex reconnection can be neglected?
So where vortex
Is there any
reconnection-
range of scales, for example, in 2 dimensions, where you can neglect vortex reconnection in terms of the properties of the turbulence?
So
You're
any
looking-
range of scale where we can observe them
No, neglect
or neglect.
the effects of vortex reconnection. So you were asking, is there an inverse cascade in 2D? And I would think that if you want to get an inverse cascade, you have to have a range of scales where you have another quadratic invariant like entropy. It's approximately conserved.
Yeah.
I think
Well,
if vortex reconnection affects the cascade over the entire range of scales, then
perhaps
I find that
it's quite possible that you do not need vortex connections at all in 2 dimensions to create an inverse cascade.
oh no. I would think that vortex reconnection would make you much less likely to get an inverse cascade because then you don't have the topological invariant.
Yes, correct. Now, the second invariant, besides the energy, which you mentioned, is a bit difficult to define here because the vorticity, strictly speaking, is equal to 0. So what is the entropy in our system? It has been argued by some that the entropy is simply the number of vortices. Clearly, if we have reconnections, we destroy or create a vortex-antivortex pair, then we change this number of vortices. My personal inclination is to say that perhaps it does not matter, because provided we don't add or destroy too many vortices out of a large system, the interaction between the vortices should produce and tend towards the inverse cascade.
We're already late, I'm afraid, although we started early, so we have to press on. So can I introduce the second speaker?